Hello, welcome to my presentation. I'm Alex Skillen. I'm a senior studying computer engineering, and I'm also one of the software team leads for Autonomy. And for my engineering honors capstone project, I decided to work with Autonomy as well as with the advice of Dr. Kurt Metzger to design an embedded system for identifying an underwater pinger's location for a autonomous boat challenge. So some background about the project. Like I mentioned, I've been with Autonomy for my entire time here in Michigan. We participate in a student design competition called Roboboat. Of the many tasks that we attempt for the Roboboat competition, one of them is the Acoustic docking challenge. And an example of that is shown on the right here. So there's a floating dock out in the water, and it's subdivided into 3 separate bays. And underneath one of those bays, there is an active pinger that's producing an ultrasonic pulse approximately once every 2 seconds or so. And so it is our objective to identify the appropriate pulse, which is at some predetermined frequency between 25 and 40 kilohertz. And then from that, identify which of the 3 bays it's coming from, and then navigate and dock in that appropriate bay before proceeding to the next part of the challenge. We've been attempting this challenge for all of the years that I've been with the team, but we've never truly reached a completed state on the project. We've run into some problems with, for example, commercial hardware that's available because the pingers are in the ultrasonic range higher than human hearing. Most standard audio equipment does not actually, it's not optimized for the range that we're actually trying to read here. And as well, we've been attempting to use 4 separate hydrophones, which means 4 audio channels, which is again, not something that's on commonly available lightweight hardware that could be integrated onto our boat. And so the objective for this honors capstone was to design a custom hardware solution that would allow us to easily integrate those hydrophone inputs into the boat so that we could use it for our robotic logic. Here's an image of our 2018-2019 competition boat. And so the 4 hydrophones that we were using are visible here on the bottom. And so they're all equally spaced horizontally on the boat. And by arranging them like this, we use time difference of arrival to establish the angle to the pinger. So when the pinger releases a sound wave, it takes some non-zero amount of time to reach each hydrophone. And so it will reach one of them first, and then from that, we can calculate the difference as it passes through each additional hydrophone. From that, we can reconstruct some information about the geometry between the pinger and the hydrophone array. And that allows us to determine an angle from the center of the hydrophone array back to the appropriate pinger. Once we have the angle, then we aim to, then we can use that with relation to what we know about our location relative to the floating dock, and then we can dock in the appropriate bay. Before embarking on the hardware side of things, I did want to verify that we could get some reasonable results. And so to do that, I simplified the model and set some bare minimum parameters. So I just used the 2 farthest out hydrophones and then evaluated at 80,000 samples per second, which is the minimum amount of sampling that we could do to properly capture the 40 kilohertz maximum signal from the pinger. What I found was that the deviation between the angle that the system calculated as the angle of origin and the real angle was less than 5 degrees for most of the situations that we would be in an actual competition situation. And so if we are expecting the pingers to be 0 straight in front of us, and then plus or minus 50 degrees on our heading, an error of 6 is not ideal, but it will not interfere with our ability to identify the appropriate bay in which to dock for the challenge. So a block diagram for the general system is that we will receive our audio inputs through the hydrophone, and that will then be amplified so that we can better read it into the computer system. Once we have converted it from the analog input to a digital signal that we can interpret on the microcontroller, we'll apply a digital filter to filter out the lower frequency noise. This could be anything from just ambient noise to the loud sounds of our motor during operation, which would otherwise interfere with and possibly drown out the pinger. Once we've filtered out the signals that are below 25 kilohertz, we can be reasonably sure that any sound that we're hearing after that is actually coming from the pingers. And once we have that, we can use a threshold to find the time difference of arrival. And once we've calculated the angle from that, send it back over USB. So to actually turn this idea into a real physical object, I designed a printed circuit board which would be able to accommodate all the 4 channels that we were hoping to use. And the microcontroller supports sampling up to 1 million samples per second, which is way higher than what was found to be necessary from testing. But using a higher value than that would produce a more accurate output. Then finally, it is supposed to be plug and play with the rest of the robot. And so to do that, it's designed to easily interface with the main computer over just a simple USB connection. That way, the main computer can be mainly focused on its tasks for operating the robot and not needing to worry about constantly sampling and figuring out where the pinger would be. With some of the changes on campus, there's much left to do. So with plans for competition thrown up in the air, the ability to really gather good data as we've suspended in-person operations has been it's been thrown a curveball. So that actual validation of the system has not been done, which is quite unfortunate because it was really, I think, one of the more fun and exciting parts of the project. So hopefully the objective then is that what was developed can be well documented and carried over with the remaining members of the team so that in future years it can be properly and fully integrated into the actual competition boat. Another challenge that I ran into many times was a temptation to overthink the problem and perhaps engineer a solution that didn't need to be there. So this is the plot that was shown earlier in the presentation with the angle error. And so initially I was tempted to increase the sampling rate significantly to try to get rid of the spikiness in the error. And that's just due to the sampling rate and the fact that we're not continuously sampling, we're sampling at discrete time steps. And that's interfering with the result. So if we could sample continuously, it would look much more like that orange line that I've layered on top of it. And so we would be able to get an extra 3 or so, we'd be able to shave off like half of our maximum angular error if we were able to sample higher. And initially I was tempted to go into that, but in discussing with my advisor for the project, he often would lead me back on track and to what things are necessary and not to actually solve the stated goal of the project, which is ultimately to produce the result needed for the competition spec. And as far as that goes, there's a path to achieve that, and we know what that would be, but we don't necessarily need to design the system to achieve perfect accuracy, because with quantized time steps, it's just not going to get there. With that, I'd like to give some acknowledgements out to Autonomy and especially Rourke Patolo for providing the background information for the project and providing a starting point and motivation for the project. And also to Dr. Kurt Metzger for providing advice throughout the life cycle of the project. With that, yeah, thank you for watching.